All right, so are you ready to have your mind blown? Today we're going deep, deep down into the universe's smallest building blocks. We're talking even smaller than atoms. You wanted to understand what everything's made of. Well, that's what we're going to be exploring. And we've got excerpts from this scientific paper. It's called Rishon theory. And we've got some YouTube videos too. The videos actually bring these theoretical particles to life. You can visually see how they could explain all these particle interactions.
It's like going to the heart of matter and seeing how it all might fit together at the most basic level.
Exactly. And the best part is we're not just talking about abstract concepts here. The videos actually show how these Rishons could be responsible for the forces that shape the entire universe. It's like watching the universe's blueprint unfold.
It really is.
Yeah. Our mission for this deep dive is to make sure that you leave understanding what these Rishons are, how they relate to the standard model of particle physics. That's our current understanding of the universe at its smallest scale, and how this alternative theory, this Rishon theory, tries to explain things like color charge and even particle decay.
It's a really compelling alternative model
Mm.
for understanding these fundamental forces and particles.
Absolutely. So let's dive in. First things first. What are Rishons? Where do they even fit in the grand scheme of particle physics?
Okay, so you know how the standard model says that quarks and leptons are the most fundamental particles? Well, Rishon theory goes a step further and says even those particles are made up of even smaller, more fundamental things. And those are the Rishons.
Okay, so we're zooming in even further than quarks and finding these tinier building blocks.
Precisely. This was an idea proposed by Hem Harari and Michael Shoup back in the 1970s. They were basically looking for a simpler way to explain the patterns they saw in quarks and leptons and their properties.
That makes sense. The universe seems to love patterns.
Yeah.
So tell me more about these Rishons. What are they like?
Well, in the Rishon model, there are two fundamental types. You have a T-Rishon, which has an electric charge of fraction of the charge of an electron. And then there's the V-Rishon, which has no electric charge at all.
Okay, so we've got our two main players. We've got T with the positive charge and V with no charge. So how do we get all the other particles from just these two?
Well, this is where it gets really interesting. The scientific paper, it uses a system of what are called ordered pairs to represent how many T and V Rishons make up each particle.
Ordered pairs like coordinates on a map. I'm not sure I follow.
It's actually a clever code. Imagine a set of instructions that tell you how many of each Rishon to use to build that particle. In this code, the first number tells you how many T Rishons there are, and then the second number, it's actually twice the number of V Rishons. So for example, a proton, might have a combination of T and V Rishons that translates into a specific ordered pair.
So different combinations give you different particles. Okay, it's starting to click. But how does this all connect to the forces that govern these particles, those forces that hold everything together?
Well, that's where the YouTube videos really shine. They dive into how Rishon interactions could actually be the driving force behind the strong force.
Ah, yes, the strong force. That's the one that binds the nucleus of an atom together.
Right.
The one that's like super glue for protons and neutrons.
Exactly. And these videos break down this specific example of the interaction between a proton and a neutron. And they show how Rishons might be the ones actually responsible for this incredible force.
Okay, this is getting good. So how does it all work? What do we actually see happening in these videos?
The videos start by showing how each individual quark, inside the proton and the neutron, is actually made up of a unique combination of T and V Rishons. And these specific combinations, determine what's called the color charge of the quark.
Hold on. Color charge.
Think of color charge as like a special property that governs how quarks interact through the strong force. There are three types of color charge, often labeled as red, green, and blue, but these are just names.
So it's more like an abstract property than actual colors.
Right. What's cool is that the videos represent these color charges visually within the Rishon combinations. It helps make it a little easier to grasp.
I love that. Visuals always help. So we see these different combinations of Rishons forming quarks, each with their own color charge, all hanging out inside the proton and neutron. What happens next?
Well, here comes the action. The videos depict the exchange of gluons between the proton and the neutron.
Gluons, those are the particles that carry the strong force, right? The glue that holds everything together.
You got it. And in this Rishon model, even gluons are depicted as combinations of those fundamental T and V Rishons. It's like everything boils down to those two building blocks.
Because it's Rishons all the way down. Rishons making up quarks and Rishons making up gluons. It's a pretty elegant idea. But what are those gluons actually doing in the videos?
This is where it gets really visually fascinating. The videos show how these gluon exchanges actually change the color charges of the quarks inside the proton and the neutron. It's like they're swapping colors, and that's what keeps everything bound together.
Wow, we can see how the strong force is working at this incredibly small scale. That's incredible. And they show these pions playing a part too, right? I remember reading about those in the paper.
Yes. The videos depict a pion. It's a type of meson, which is made of a quark and an antiquark. And it acts as kind of a go-between in this strong force interaction. It carries the color charge between the proton and neutron and kind of helps mediate the strong force.
So we've got pions made of rishons shuttling this strong force between the proton and neutron and changing the colors of the quarks along the way. It sounds like a complex dance is happening inside atoms, and the videos make it all so much more tangible.
It's a beautiful illustration of how these tiny particles might be orchestrating one of the most fundamental forces in the universe. And this is just one example of how the Rishon model tries to explain these particle interactions. And it gets even more intricate when we look at particle decay.
Particle decay. That's where particles transform into other particles, right? Like a subatomic magic show.
You could say that. And the videos actually dive into a specific example, the decay of a top quark, also known as a T-quark.
Okay, so now we're talking about top quarks. Those are some of the heaviest fundamental particles that we know of.
Right.
Quite a jump from protons and neutrons.
Yeah. They are indeed. And their decay is a complex process, but the Rishon model provides a whole new perspective on it. The videos break down how this T-quark is initially made up of a specific set of Rishon combinations. It includes what the video creator calls a generic D-quark, along with some scalar bosons, which you can think of as particles responsible for giving mass to other particles, and even particle-antiparticle pairs.
Wow, so even these heavy T-quarks are built from those same TMD Rishons. It really shows the potential of this theory to explain such a wide range of particles. But how does the T-quark actually decay in this model? What's happening at the Rishon level?
Well, the videos illustrate how the T-quark emits a W boson. This is another fundamental particle, one that's crucial for what we call weak interactions. These govern things like radioactive decay.
Right, so another key player enters the scene.
And of course, in this model, even the W boson is depicted as a specific arrangement of rishons. This emission of the W boson leads the T-quark to transform into a bottom quark, also called a B quark. It's fascinating to see how the videos really meticulously account for all of what are called the quantum numbers throughout this entire process.
Quantum numbers. Refresh my memory on what those are.
These are essentially a particle's ID card. They describe properties like electric charge, spin, and something called weak charge, which is kind of like electric charge, but governs the weak interaction instead. And these numbers, they have to remain balanced in any interaction or decay. And the videos show how the Rishon model manages to account for all of them.
That's really impressive. So even though this Rishon model is a completely different approach, it still manages to line up with what we already know from the standard model.
That's the remarkable part. It shows the potential of this model to maybe offer us an even deeper understanding of the universe, while remaining consistent with everything we've observed. And there's more. The video creator mentions plans to further explore things like isotopic spin, flavor, and color in more detail in some future videos.
Wait, hold on. Isotopic spin, flavor, color. Those are some pretty complex concepts, even for someone who's been trying to follow along. Can you give us like a quick breakdown of what those terms mean before we move on?
Absolutely. So let's start with isotopic spin, or isospin for short. It's like an extra layer of identity for particles. It helps us distinguish between particles that are very similar in other ways, like protons and neutrons, for example. They both have nearly the same mass, they're both made of quarks, but they have different isospin values, and this helps explain their slightly different behaviors.
So it's like a hidden code. That tells us more about how they act.
You could think of it that way. Now, flavor, that refers to the different types of quarks. There are 6 flavors in total: up, down, charm, strange, top, and bottom. And just like isospin, each flavor has its own set of properties that affect how it interacts with the fundamental forces.
So we got these 6 flavors of quarks, each with its own, personality. And then isospin comes in, adding another layer of complexity. It's like adding different spices to a cosmic soup.
I like that analogy. These concepts, along with color charge, are fundamental to understanding these intricate interactions that govern particle behavior. And if the Rishon model can successfully explain all of this, well, it could be a major leap forward in our understanding of the universe.
This is mind-blowing. We've gone from these tiny rishons to protons and neutrons to pions, W bosons, top quarks, bottom quarks. It's like exploring a whole new universe inside our own. But before we go too far down the rabbit hole, let's make sure our listener is still with us. What are like the key takeaways that they should be grasping so far?
That's a great point. Let's synthesize and give our listeners some food for thought.
Sounds good. I feel like we've covered a lot of ground here.
So you've gotten a glimpse into this really fascinating, though still theoretical, world where everything comes down to these tiny rishons. It's a different way of looking at the universe's building blocks. And while it's not widely accepted yet, it offers these intriguing explanations for how particles interact and even how the universe might be structured.
It's like learning a whole new language. To describe the universe, instead of letters, we have T and V rishons. And just like letters combine to make words, these rishons combine to form the particles and forces we see all around us. And those YouTube videos, they really brought this concept to life. Seeing those rishons interacting and changing color charge was amazing.
Visualizations can be so powerful for understanding these really complex scientific ideas. It helps us make connections that might be hard to grasp otherwise.
Absolutely. If I had learned particle physics like this back in school, I might have actually enjoyed it more. But before we move on, I'm curious about those ordered pairs we talked about. The way they represent the number of each type of rishon in a particle. It seems almost too simple. Is there more to it than just counting rishons?
There might be. What's fascinating is the author sees a potential link between these ordered pairs and the very structure of space-time itself.
Wait, space-time? We're talking about the fabric of the universe here. How can these tiny rishons, things smaller than quarks, be connected to something so vast?
It's a bold idea, and the author draws on the work of physicist Piotr Zędzikowski, who has really explored this connection between space and matter.
Okay, I'm all ears. Tell me more about this connection between rishons and space-time.
Well, the author suggests that the numbers in those ordered pairs, the ones that represent the T and V rishons, might correspond to the number of space and momenta vectors as Zędzikowski proposed. It's a complex idea, but basically it suggests that the very building blocks of matter are also the building blocks of the space they exist in.
Whoa. It's like those rishons are weaving the fabric of space-time as they create particles. It's really making me rethink everything I thought I knew about the universe. But if rishons are part of the structure of space-time itself, does that mean they're not actually physical objects in the way we typically think of them?
That's exactly what the author proposes. Rishons in this model aren't objects sitting in space-time. They're more like dimensional components of the space-time structure that forms those quarks and leptons.
Okay, I'm going to need a minute to wrap my head around that one. It's like saying that rishons are more like the threads in a tapestry than the beads sewn onto it. They're not separate, but rather like an integral part of the fabric itself. It's a fascinating concept. But it does raise a lot of questions. Like if rishons aren't traditional particles, how can we even detect them? How can we test this theory?
That's the challenge with any theory that goes this deep. It demands new experimental techniques, new approaches, ways of thinking beyond our current methods. But that's also the beauty of science. It's always pushing the boundaries, always searching.
You're absolutely right. The quest for knowledge is never ending. And who knows, maybe someday we'll have the tools to directly observe these rishons and see if this model holds up.
Always more to learn. And exploring these different perspectives enriches our understanding. It's what makes this kind of deep dive so fascinating.
I couldn't agree more. So where do we go from here? We've seen how rishons might explain the strong force and gotten a glimpse of how they could account for particle decay. What other mysteries of the universe might this theory help us unravel?
Well, the creator of those YouTube videos mentioned plans to further explore color charge using this rishon model.
Color charge. That's got to be one of the trickiest concepts to grasp in particle physics. If this model can shed more light on how it works, that could be a major breakthrough. But it's not just about explaining things we already know, right? This kind of new model could potentially lead to new discoveries, couldn't it?
It does. It makes you wonder, do you think a model that visually represents these forces in such a direct way could lead to those new discoveries? Or even a deeper understanding?
I think it absolutely has that potential. If we could actually visualize how these rishons are interacting, combining to form different particles and forces, it could spark all sorts of new insights. We might see patterns and connections that we just missed before. It could even inspire new experiments or new ways of thinking about the universe.
It's exciting to consider the possibilities.
It really is. And I bet our listener is feeling that same excitement as we explore this rishon theory. But we're not quite done yet. Remember those future videos the creator mentioned? The ones about isotopic spin and flavor? I'm really curious to hear more about those.
Those are really key concepts. These concepts, along with color charge, are essential for understanding the intricate interactions that govern how particles behave. And if the Reshon model can explain all of this, well, it could really be a major leap forward in our understanding of the universe.
It sounds like there's still so much to explore with this Rishon model. It's like we've just peeked through the doorway of a vast, uncharted territory.
It's a thrilling journey, and we're all along for the ride.
Well said. We've taken our listener on quite the journey today, from these incredibly tiny Rishons to the very fabric of space-time. But we can't leave them hanging. We need to give them some resources to continue exploring on their own. What would you suggest?
Well, those YouTube videos we mentioned, those are a great place to start. If you want to, really delve deeper into this whole Rishon theory, they do such a good job of, visually explaining all these concepts. And of course, there's the paper, Rishon Elements Decay Modes, if you want to explore the theory behind it all.
It really makes you think differently.
Yeah.
About what our universe is made of.
It does, and that's what makes these deep dives so rewarding. We can explore these models that are not, widely accepted yet, but they offer such a fresh perspective on some of the biggest mysteries in physics.
And this model is still evolving. The video creators' work, exploring things like color charge, isotopic spin, and flavor within the Rishon model. That's really intriguing. It'll be interesting to see where it goes.
It's like watching a scientific theory get built right in front of us. It really highlights how science is always evolving, always seeking new explanations and pushing the boundaries.
And that's what makes it so fascinating. So to our listener, we encourage you to keep that curiosity burning. Don't be afraid to explore these unconventional ideas and challenge the established way of thinking.
The universe is full of mysteries, just waiting to be unraveled. Keep asking questions, keep exploring, and keep that thirst for knowledge alive.
That's the perfect thought to end on. Thanks for joining us on this incredible deep dive into the world of Richness. Until next time, keep those minds curious and those imaginations firing.